So when we look at the circled area, we are looking at the nephron loop. It is important to understand that the descending limb of the nephron loop is permeable to water, so about 15% of the water is absorbed, but it's not very permeable to solutes. And then the ascending limb, as it goes back up where the arrow is pointing, is not permeable to water, but it is permeable to solutes. So what happens is the concentration of this filtrate coming from the proximal tubule into the nephron loop increases as it goes down toward the hairpin as water leaves. So it's the most concentrated at the bottom of this hairpin, but as it comes back up, it's impermeable to water, but solutes leave. So as it comes back up, it gets less concentrated as solutes can leave, but water can't. So you've got roughly the same concentration here at the beginning as you do at the end of the loop, and it comes back up. And that is going to be very important for physiological implications that we are going to talk about, as this helps to maintain the osmolarity of the renal medulla as solutes come out and pepper this area of the medulla around it. The symporter that largely moves solutes out of the ascending limb is a sodium-potassium 2-chloride symporter. So it pulls 2 chloride ions and a sodium and a potassium out. And notice that they're different sizes. These are largely located in what we call the thick limb of the ascending. So the thicker one is where this is at. There's also some paracellular reabsorption between cells of sodium, potassium, calcium, and magnesium. So you can see a little bit of this. There's the sodium 2-chloride potassium symporter, and there's some of the cations going through paracellular reabsorption. So we see some of those potassium ions are secreted back in as sodium and chloride are reabsorbed into the blood. The early distal tubule is different than the late distal tubule. So the distal tubule at the end works more like the collecting duct. So we're going to look at the early distal tubule. There's a lot of obligatory water reabsorption. So we reabsorb sodium and chloride and water follows. This is also where parathyroid hormone tends to bind so that we can reabsorb calcium whenever the body needs more. So the body is concerned about calcium for muscle contraction, for blood coagulation, and also we store a lot of calcium and minerals in bones. So we have calcium reabsorption and phosphate secretion there when parathyroid hormone PTH is bound. So those sodium chloride symporters reabsorb sodium and chloride, and 10 to 15% of water is reabsorbed there as it follows the sodium chloride. The late distal tubule functions along with the collecting duct, this long area that supplies sometimes more than one nephron, but there are two important types of cells located in the late distal tubule and the collecting duct. Principal cells, which have receptors for both antidiuretic hormone and aldosterone, which help to maintain sodium and blood volume, as well as intercalated cells that reabsorb potassium and bicarbonate ions and secrete more hydrogen. Principal cells reabsorb sodium and secrete potassium too. So we'll see as we look at diuretics as well, lots of diuretics are potassium secreting. But there are aquaporin 2 channels that are inserted into those principal cells whenever ADH, antidiuretic hormone, is bound, and that allows us to reabsorb more water. So we saw aquaporin 1 channels that reabsorb water that are just located in the proximal tubule, but when antidiuretic hormone is bound, it makes urine more concentrated and allows us to bring in more water by putting in aquaporin 2 channels. Aldosterone is more focusing on sodium, so we have sodium and chloride reabsorption and potassium secretion, and water can also follow through some of those aquaporin 2 channels in principal cells when they are secreted. So if there's increased osmolarity of plasma and interstitial fluid, that means there's less water and it's more water withdrawing, pulling water out of cells, maybe dehydrated. This is detected by the hypothalamus, which is our thirst center. It triggers the posterior pituitary to release antidiuretic hormone. This acts on the principal cells and allows us to insert those aquaporin 2 channels, which allows facultative water reabsorption. So based on the needs of the body, instead of water following salt, this is where we see a lot of our facultative water reabsorption. Then as we have more fluid retention, the osmolarity of plasma goes down and we return back into homeostatic mechanisms. And this is or not mechanisms, but ranges. And this is where we see blood pressure also affected with those fluid compartments. So the big picture of reabsorption and secretion, we see reabsorption is a large portion of the proximal tubule, but we secrete hydrogen, nitrogenous waste like urea and uric acid and some drugs. The descending limb of the nephron loop is permeable to only water. The ascending limb is permeable to only salts like sodium chloride, and potassium ends up being secreted again. The distal tubule, we have some obligatory water reabsorption, so 10% of water, sodium chloride, and some calcium as parathyroid hormone is bound. The late distal tubule and collecting duct, we have some facultative water reabsorption when ADH is bound. We have aldosterone binding sites. Most of the remaining water, sodium chloride, and bicarbonate ions reabsorbed, and hydrogen secreted.